Hello. Today we're going to talk about, we're going to review a little bit about speed and velocity. But mostly I want to talk about acceleration. Now, one of the problems that we'll have in this class is that a lot of the terms that we use scientifically already have meanings in common language. And when people say acceleration, they almost always mean speed up. But that's not the only way you can accelerate. Acceleration is a change in velocity, and there's more than one way of changing velocity. And this, in fact, is one of the standards that you need to know, which is that acceleration is the change in velocity over time. But that can mean much more than just speeding up. Now, a little review to begin. We've said that to describe motion accurately, you need to have a frame of reference. You need to be able to describe motion in terms of the change in position relative to a reference point. We're all moving. Even when we're sitting still, we're moving based on a reference point somewhere in outer space. But the best frame of reference you can have is something that is standing still. If you're in a car or a train and you can see an object, a tree or a fence go by you, if it goes by you very quickly, it's not actually moving. You are. But from your frame of reference, it appears to be moving. The speed of that motion can tell you how fast you're going. What would be the best frame of reference to use to judge the speed of a car if you don't have a working speedometer? Looking at the person next to you, well, they look like they're sitting still. Watching a car go by you, you're going 70 miles an hour, it's going 80 miles an hour. It looks like it's going 10 miles an hour. That's not really going to tell you how fast you're going. You don't know how fast they're going. But something sitting on the side of the road, that would be a good clue. So the first definition we had was distance. Distance is how far an object moves from point A to point B, and it's measured in meters. The scientific method uses meters, about 3 feet. This doesn't tell us the direction, though. Distance is a scalar quantity, so it only tells us magnitude. We could say I moved 10 meters, but I don't know if I moved that way or which way. For that, I need to know displacement. And displacement is not just the distance that I've moved, but also the direction that I've moved. So your displacement is essentially where you end up compared to where you began. Now, distance and displacement could be virtually the same thing. I could go 10 meters north, and my distance would be 10 meters. My displacement would be 10 meters north. However, I could then walk back to where I began. I would have gone a distance of 10 to get out there and 10 to get back for a total distance of 20 meters. And my displacement would be 0. I'm right back where I started from. Displacement can never be greater than distance because you have to travel that distance. That would be your displacement, a straight line. And as soon as you start taking turns or going in circles, your distance never goes down. It just keeps going up. But your displacement could go down as you go back toward where you started. Our first formula is a pretty easy one. Speed is distance divided by time. That would be your instantaneous speed. If you wanted to know the average speed, take the total distance that you traveled. Let's say you drive from Sanford all the way to North Hollywood. Pretty big distance. And then divide that by how long it took you. Now, in that time, you're almost certainly going to have to stop for drinks and food and probably take a rest and get some gas. You're not going to be going at the same speed. You're going to end up with an average speed that's probably much lower than you were going at any point in time. But that's how average speed works. Velocity is another one of those words that gets confused because people think of velocity as very fast speed. Velocity can be slow. It's just speed plus direction. So speed would be 10 miles an hour. Miles, distance, hour, time, distance over time. Velocity would be 10 miles an hour west. And we talk about distance and velocity. They have certain things in common. They both measure how fast something is moving. But they're different in that velocity includes direction and speed does not. In this way, velocity is more like displacement and speed is more like distance. Speed and distance are both scalar quantities, just magnitude. Velocity and displacement are vector quantities. They have direction as well as magnitude. Now, why this is important is that we'll get to acceleration. Acceleration is not necessarily a change in speed, but it is a change in velocity, which means since velocity includes direction, you can accelerate simply by changing your direction. So now we finally get to acceleration. This is the rate at which velocity changes. And this could be a change in speed, either going faster, the way most people think acceleration is, or slowing down. You're changing your velocity, therefore you are accelerating. Very few people would consider slowing down accelerating in common language, but in scientific language, it is. Sometimes we call it deacceleration. Some people call it negative acceleration. That's fine, but it is acceleration. And so is staying at the same speed. Let's say your car is on cruise control and you just make a turn. You are accelerating. And I think one of the clues you can have about acceleration is you feel it. You don't feel the fact that the Earth is going at a tremendous rate of speed by spinning and going around the sun. You don't feel it because it doesn't change. If the Earth were to suddenly come to a stop, if it were to stop spinning, we'd all be killed instantly. The wind would suddenly be going thousands of miles an hour and it would wipe everything clean. So let's hope that never happens. That would be like being in a car. Car's going 90 miles an hour at a steady speed. You don't feel it, but if it hits a wall for a very brief moment of time, you would feel it. So acceleration, you can feel. And if you're in a car that's going at a regular speed on cruise control and it makes a sudden turn, you get thrown one way or the other. You'll notice that. You'll feel it. In an airplane, you feel taking off, you feel coming down to a stop, but you don't really notice it if it's a smooth ride when you're going 600 miles an hour. And one example of acceleration that most people would not think of with the word acceleration is a merry-go-round. And let's face it, this is the world's least exciting carnival ride. You are constantly going in a circle. You're changing your motion every second, and you are accelerating. It gives that ride what little enjoyment it has. And if you're on the right horse, it's going up and down, and it's a boring ride. A more exciting ride would be the roller coaster. And most people would say roller coasters are going 100,000 miles an hour. And they are probably going closer to 30 miles an hour. If you're in a car going 30 miles an hour, you probably feel like you're watching paint dry. It's painfully slow. On a roller coaster, you're in this little car, and you are just constantly turning and twisting and going upside down, and it feels like you're going really fast. If this ride were just a straight track and you just were going like this, there'd be no acceleration at all. Very boring. So by just making a lot of turns and occasional changes in speed, but not as many as you would think, you feel the excitement because you're feeling that acceleration as you get tossed back and forth. So how do we calculate acceleration? Well, first of all, we're not going to calculate the kind of acceleration where the speed stays the same, but the direction changes. I'm sure there is a formula, but that's like college physics. But we can look at something speeding up or slowing down. The formula for that is the change in velocity divided by the time it takes to make that change. Suppose I'm in a car going 30 meters per second, and I come to a stop. There's a stop sign. So it takes me 10 seconds to go down to zero. My acceleration would be 30 meters per second, no, 0 meters per second, minus 30. My final velocity was 0. So 0 minus 30 divided by 10. And what you end up with is negative 3 meters per second per second. Now, it's important to remember that. Meters per second per second. What does that mean? It means every second I'm going, if it's negative 3 meters per second, I'm going 3 meters per second slower than I was a second earlier. I decide to hit the gas pedal, go forward. It takes me 10 seconds now to go from 0 to 30 meters per second. So my final velocity is 30 meters per second. My initial velocity was 0. 30 minus 0 divided by 10, again, gives me not a negative number this time, but a positive number, 3 meters per second per second. That's another clue, by the way, for finding the correct answer on an acceleration problem. Don't put down 3 meters per second as an acceleration. That's a speed. That just tells you every second you're going 3 meters. 3 meters per second means my first second I'm going 3 meters. My second I'm going 6. My third, I'm going 9, 12. You're speeding up. You're accelerating. One of the things that we'll get into pretty soon is the idea of gravity. When you jump out of an airplane, hopefully with a parachute, you're falling at 9.8 meters per second per second. The first second, you travel 9.8 meters. That's nearly 30 feet. The second you're going faster. It's that 9.8 plus another 9.8 meters per second. You've doubled your speed. The next second, 9.8 plus 9.8 plus 9.8, you start picking up some real serious speed. And there comes a certain point after a few seconds, you had better have a parachute because you're going really fast. That speed does reach a limit, which we will talk about a bit more next week. So the big takeaway from this is please understand that acceleration, a change in velocity, and since velocity is speed and direction, either a change in speed, a change in direction, or a change in both will give you acceleration. Thank you.